So looking at page 51, integrals involving trigonometric identities. The first thing I'm going to do is, and we've kind of alluded to this, but I wanted to kind of formally address it, talk about the Pythagorean identity. So if we have a unit circle, so a circle with the center at the origin and a radius of 1, any radius around that circle obviously is going to be 1, but we can decompose any point along the circumference of that circle into components. All right, now any coordinate in space is x comma y, but specifically in the context of the unit circle we can go a little bit further than that. All right, so we have x, the horizontal distance of x, right? Because remember, horizontal distance from the y-axis to a point in space is known as x. Vertical distance from the x-axis to a point in space is known as y. All right, and so the relation here is that x squared plus y squared is equal to 1. All right. Now we could also follow that up with some trig relations, and that is, if we assume a reference angle theta here, the cosine of theta, remember SOHCAHTOA, cosine is adjacent side divided by the hypotenuse. So the cosine of theta would be x over 1, which means that x is equal to the cosine of theta. All right. So one way of representing the x coordinate around the unit circle would be with the cosine of whatever the reference angle is. All right, cosine of theta. Now, we could also do the same thing with the sine ratio. Sine is opposite over hypotenuse, so sine of theta is equal to y over 1. All right, opposite over hypotenuse, opposite y, hypotenuse 1. So therefore, y is equal to the sine of theta. And when you get to polar coordinates, you'll expand on this, because it isn't always the case that you have a radius of 1. Sometimes the radius is 2 or 10 or whatever. And so that'll impact the value of x and y. But for now, we're only working with the unit circle, and that tells us that y is equal to the sine of theta. All right, so using that Pythagorean identity, I'm just going to swap the order here a little bit. Apologies, a little sniffle. Knowing that x is equal to cosine of theta in the unit circle, I can replace the x with a cosine theta. Y is equal to the sine of theta in the unit circle. Very important that you stay with that idea that in the unit circle. You know, x is not always equal to the cosine of theta. Y is not always equal to the sine of theta. It's only when it's in the circumference of the unit circle that that relation is true. All right, so cosine squared theta plus sine squared theta is equal to 1. All right, so that's a little pre-calc review for you. All right. I know that when, I taught pre-calc for years, so, and I still teach pre-calc. The theory, unfortunately, is one of the first things to go when you're pressed for time. You know, it ends up being kind of like, okay, well, we'll just focus on the skills because that's what you need for calculus. And a lot of the why part of it takes a back seat to the how. All right. So if we know now that that relation of cosine squared theta plus sine squared theta equals 1 is a true statement, then we have some corollaries that come from that. And one of which is that the sine squared of theta is equal to 1 minus the cosine squared of theta. You get that by just subtracting cosine squared theta from both sides. So that gives you this rule here. If you subtract the sine squared theta from both sides of the equation, you get this rule. All right. Something that's not listed here is something that we talked about and is very helpful, and it comes up in a couple of pages. If you divide every entry here, or each term, by cosine squared, cosine squared divided by cosine squared is equal to 1. Sine squared divided by cosine squared is equal to tangent squared. 1 divided by cosine squared is equal to secant squared. So a corollary to the main Pythagorean identity is another Pythagorean identity, just a little less recognizable from the circle, and that is that 1 plus tangent squared is equal to secant squared. All right. In the same vein, oops, I meant to write sine. If you divide each term of the Pythagorean identity by sine squared, you're going to get cosine squared divided by sine squared, which is cotangent squared. Sine squared divided by sine squared is equal to 1, and then 1 divided by sine squared is equal to cosecant squared. All right. So, yeah, that's useful information. I forget which page it is. It's like page 48, maybe page 49. But I have all those reference tables. It's at the end of the Unit 1 packet. Kind of a prep for the Unit 2. So if you take a look at that, you'll see all these rules are there. It's just, I like to introduce it so that you know what you're looking at when you see it. In theory, again, this is the kind of stuff you should have seen before, but I can't take the chance, And also, this is a video that you can speed up or slow down or repeat or skip, So you look at it and say, oh, I already know this, so skip, Anyway, so, let me clear this. This is distracting. So what we're going to do is apply some Pythagorean identities and some other identities to help us integrate. All right, and so we'll work through them. I don't want to say one at a time, but in order of simplest to most complicated. How about that? So some helpful guidelines. So you'll notice it doesn't say rules. It's kind of along the lines of the tips from integration by parts, where it's like, well, these may work, but then again, you may have to try something else. All right, so if the power of cosine is odd, save one cosine factor and convert the remaining factor to sine. And if the power of sine is odd and positive, both are positive, save one sine factor and convert the remaining factors to cosine. The idea behind this is if you have an odd power, like cosine cubed in the first example, if you factor it by separating out one cosine and the other factor would then therefore be cosine squared, you'll be able to apply one of these rules. All right, that's the idea. All right, so now just because these say x in the rules doesn't mean necessarily that it only works when the argument or the reference angle is x. I mean, it's just really anything that follows this form is going to be a true sentence. All right, so for example, if I were to say sine squared of x squared, by this relation, we should end up with 1 minus cosine squared of x squared. The only time these kind of things, these rules, can be a little iffy is if you throw in a, oh, I didn't want to highlight the whole thing. You throw in some function that maybe has I've drawn a blank on the word here, discontinuity. Yeesh. I got there eventually, but it took way too long. So this is not a proof, but it's justification. You know what? Let me do it on Desmos because it's easier to make the notation match up. So I'll type in sine squared of, and even Desmos sometimes has an issue with powers of trig functions, but oops, got to get out of the exponent. All right, but the good thing about obviously Desmos is the copy paste. All right, so I'm going to change that to a cosine. Now you'll notice I don't think I mentioned this. I mean, we're like 50 pages into the packet, and I don't think this ever came up. But you'll notice in Desmos, and I'll just do this in a separate line, that when you start typing, it's in italics. But when Desmos recognizes it as a mathematical function, it turns italics into ordinary font. That's how you know you typed in something that Desmos understands. So like LO, well, I'm going for log. So right now it thinks L and O are constants. But once I type in G, it knows I'm talking about a log. All right, so I'm pretty confident that I just typed in these two things correctly. So what I like to do here is turn one of them off, or well, actually, sorry, turn both of them off, and then turn them on one at a time and see if they match up. And if it's not obvious, and you know, sometimes it's a little inconsistent, but sometimes it's pretty obvious. This is like right in the wheelhouse of my color blindness, like the purples. So, yeah, it's just kind of a weird thing. One day I went to work wearing what I thought were gray pants, and they were bright purple. It's fun. They're like, oh, nice purple pants. I'm like, nah, they're gray. No, they're not. So if that's an issue for you, what you can do is change the thickness. If you long press on the icon, the graph icon on the left, it's defaulted to 2.5. Make it something thicker, like 5, so that it becomes clear that it's overlaying on top of the other graph. All right, so again, not a proof, but a demonstration. All right, so it shows that the two graphs are, at least in the eyes of Desmos, equivalent to one another. All right, so what we're going to do is try to apply that relation here in number 1. Because I can't take the antiderivative, like me personally, can't take the antiderivative of cosine cubed. I'd love to be able to use something like U-Substitution, but what am I going to call U? If I call 5x U, I'm not going to improve the situation because it's not going to help me cancel out the thing that I have trouble integrating, which is the cosine cubed. If I call cosine cubed, or even cosine U, the derivative of that's going to involve a sine. There's no sine to cancel out. It's going to introduce something while canceling out something else. I'm going to have an integral that contains both u's and x's. That's no good. So what we're going to do is rewrite this as cosine squared of 5x multiplied by cosine of 5x dx. That's what I mean by saving a cosine. This is the cosine that I'm saving. I'm hanging on to that. But this one is a power of 2. I could use the Pythagorean identity to swap that out for a 1 minus sine squared of 5x. And you might look at that and say, well, how's that going to help? Well, that's the thing. It may not, but if it does, you'll find out really pretty much in the next step. All right, so the idea here is to use some sort of technique of integration that we're familiar with, and at this point you're kind of fortunate because we're only familiar with general rules and U-substitution and integration by parts. So those 3 concepts. One is like an all-encompassing concept, so no help there, like a rule. All right, maybe there's a rule out there that accounts for this integral, but I don't know that rule. U-substitution or integration by parts. Well, if I have a choice in the matter, I'm going to go with the simpler approach, and then if that doesn't work, I'll try something more complicated. So U-substitution. Well, in U-substitution, we know that we like to swap out the more complicated piece. But in addition to that, we need whatever we select as U to differentiate in such a way that it'll help cancel out the thing that we did not select as U. All right, so if I make the entire 1 minus sine squared 5x into U, that's going to be a problem. Because that's going to differentiate, and you know, the strength in being able to take derivatives is really what's going to come to the forefront here. Hopefully your Calc 1 teacher told you that. That's what I tell all my Calc 1 students. It's like, you'll be really good at integrating if you become really good at differentiating. All right, so there's chain rule here. If you were to differentiate 1 minus sine squared 5x, you would get, well, the 1 would go away. You get negative 2 sine of 5x times, then you'd have to take the derivative of the sine, which is cosine of 5x, then the derivative of the 5x, which would be 5. So we'd be looking at negative 10 cosine 5, cosine 5, sine, let me say that again, negative 10 sine 5x cosine 5x. I was getting tripped up on the 5x. Anyway, and that's a lot. Yeah, it would help us cancel out the cosine 5x, but it would introduce us to a negative 10 sine 5x. So it would pull something out, but replace it with something just as bad. So that's not going to be a way to go. Now, if you can't talk that out, or at least recognize that on site, then you got to write it out. And it takes a couple minutes. As it turns out, if we let U equal the sine of 5x, the derivative of that is going to be cosine of 5x times 5. So 5 cosine 5x dx would be equal to du, which is not what I just wrote. Yeesh. Du. All right. Now I need to get rid of the cosine of 5x dx. So I'm going to divide out the 5. And now I have something a little bit cleaner. I'm going to replace the sine of 5x with a u. So we're looking at 1 minus u squared, and then I have the 1/5 du replacing everything else. So I'm going to write this as 1/5 minus 1/5 u squared du, integrate 1/5 u minus 1/15 u cubed plus c, and then replace my u. So 1/5 u becomes 1/5 sine of 5x minus 1/15 sine cubed of 5x plus c. And you can verify that, but you know, that's something you could do separately. All right. So you see there's a lot going on there, but manageable if you get off to a good start. Looking at number 2, it's a question of, all right, well, I mean, I'm going to say the same thing fairly frequently. It's a question of, okay, where do I start? Is it just straight U-substitution? Do I have to use an identity first and then go the substitution route? All right, well, you play it out in your mind. If I let u equal cosine, that'll give me a negative sign when I differentiate. That's not going to cancel out a sine squared. Same idea if I let u equal sine, it'll give me a cosine that's not going to cancel out cosine cubed. If I let u equal cosine cubed, that's going to give me 3 cosine squared x times negative sine. that'll cancel out part of the sine and introduce a cosine squared, making matters worse. If I let u equal sine of 2x, sine squared of x, I'll get 2 sine x cosine x. That'll cancel out part of the cosine cubed, but not all of it, making matters worse. All right, so we're not ready for a u sub. So we want to manipulate this a little bit. I could replace the sine squared with a 1 minus cosine squared. But then I'll be kind of in the same boat as I was with number 1 initially, in that I'll have everything in terms of cosine and nothing to cancel it out with. So what I'll do is follow the strategy. I see an odd power for cosine. I'll save a cosine. Swap out the cosine squared for a 1 minus sine squared. Everything else comes along for the ride. I can multiply these two things together. Sine squared x minus sine to the 4th x. Now that I've cleaned it up a little bit, I can start my U-substitution investigation. And if U-substitution doesn't work out, then I would move on to integration by parts. It didn't come up in number 1 because it worked with U-substitution, but it might have, and if it did, then I would have to move on to integration by parts. So looking at this, I would start simple. I'd say, okay, well, if I let u equal cosine, well, that's not, the derivative of cosine is negative sine. That's not going to cancel out the other binomial. If u is equal to sine, that's cosine as a derivative. That's going to do the trick. So I can swap out cosine x dx with a du, and each instance of sine is going to get replaced with a u. So u squared minus u to the 4th du. So 1/3 u cubed minus 1/5 u to the 5th plus c. So 1/3 sine cubed of x minus 1/5 sine to the 5th of x plus c. And there it is. All right. But it's that first step. Watch that first step. It's a doozy. You know, that old thing. That old chestnut. All right. So that's page 51.